or a vibrating system with three different methods. The first one is equilibrium method, or it is called as a D'Alembert's principle. The second method is energy method, or it is also called as Newton's method. Please make a note. Second method is also called as energy method, is also called as Newton's method. Please write down in the bracket Newton's method. The third one is Rayleigh's method. Okay, and all three cases we are getting the same answer for natural frequency as well as angular velocity, right? And we'll move on to the next concept. The next concept, equivalent stiffness of the spring combination. Equivalent stiffness of the spring combination. Equivalent stiffness of spring combination. Spring combination. Equivalent stiffness of spring combination. Equivalent stiffness of spring combination. Okay, next line. Certain system have more than one spring. Certain system have more than one spring. Full stop. The springs are joined in series or parallel. The springs are joined in series or parallel, or both. Or both. Full stop. They can be replaced by a single spring of the same stiffness. They can be replaced by a single spring of the same stiffness. They can be replaced by a single spring of the same stiffness, as they all show the same stiffness. Same stiffness. Okay. If you have more than one spring, you can have a combination in series as well as parallel, right? Series as well as parallel. At that time, if you have more than one spring, now we need to find out the effective spring stiffness for the combination. The first case number one, is springs in parallel. Springs in parallel combination. Springs in parallel combination. If the springs are in parallel combination, let us take the figure. So this is what the combination. We have the first spring and we have the second spring. Okay, we have spring constant for first spring is K1, spring constant for second spring is K2, and it is connected to a common mass M. Now the springs are in parallel combination. So if you have a single spring, you know how to write the spring stiffness equation, right? Is equal to mass is connected to K, then K into X is nothing but a spring force, right? But here, if you connect two different springs, now if you want to find out the value of stiffness or the combination of stiffness or effective stiffness of both K1 and K2, because if you apply the load on M, it moves an x distance. X distance is common for both K1 and K2 because it is the load what you apply on mass will be shared by two different springs, that is K1 and K2. But the displacement is X, it is common for both, but we need to find out the effective stiffness due to K1 and K2 in this case. Okay, so effective stiffness, write down The deflection of the individual spring is below this. The deflection of the individual spring is equal to the deflection of the system. The deflection of the individual spring is equal to the deflection of the system. Means the displacement or the deflection of K1, K2 are equal, and it is equal to the deflection of the system, entire system, right? So write down the deflection of the individual spring is equal to the deflection of a system. That's why. So you can write the equation K1, first one, displacement of K1 into X. X is the deflection of the M. Let us write it as X, okay? Deflection of M, X distance. X plus K2 into X. Displacement is same. It is equal to effective stiffness, combination of both E, KE into X. Here X is common for all. If you move X distance by mass M, the displacement for K1 is also X, K2 is also X. That's why X is common term, K1 into X. The force on first spring, that is K1 into X. Force on second spring, K2 into X, is equal to the net force acting on the mass F. That is KE into X. KE into X. For the parallel combination. Understood? Here X, XL get cancelled. Okay. And the final answer. K1 plus K2 is equal to KE. Now, how do you find out the effective stiffness of the springs in parallel? By adding individual stiffness. That is the equation for parallel. Where write down below this, where KE is equivalent stiffness, or it is called as effective stiffness, or effective stiffness of the system. Effective stiffness of the system. Below that, K1, K2 are the stiffness of the springs. K1, K2 are the stiffness of the spring. Next, X is the deflection of the system. Small x is the deflection of the system. KE into X, KE into X, KE into X is force on the system. See, if you apply force F, this force will be divided F1, F2, right? What is F1? That is a spring force. K1 into X. F2, K2 into X. So K1 into X, K2 into X. It is equal to the total force. Total force is KE into X, effective stiffness into X. So by that you can find out the equation for the effective stiffness of the spring in parallel combination. Okay. Write down the last sentence. Thus, the equivalent spring stiffness is equal to. Thus, the equivalent spring stiffness is equal to the sum of the individual spring constant. Thus, the equivalent spring stiffness is equal to the sum of the individual spring constant or stiffness. Sum of the individual spring constant or stiffness. Next, the second case. Springs in series combination. Let's have a figure. We have a spring 1 and we have connected another spring 2. This is what M. This K1 K2. We need to find out the value of effective spring stiffness. This is moved at a distance of x when you apply the load F. Copy the figure. Can anyone answer? Am I audible?
Yes, sir.
Is the screen is visible?
Yes, sir.
Okay, now it is 37. 6 members have joined late. Okay. The figure is K1, K2, and M. The springs are the two springs are there. It is combined together in series. Now we need to write the equation for this one. Write down the total deflection of the system is equal to the sum of the deflection of individual springs. Below this, write down the total deflection of the system is equal to the sum of the total deflection of the system is equal to the sum of the deflection of the individual spring. Sum of the deflection of the individual spring. Look at this. Let us consider the mass is moving at a distance of x. Let I repeat the sentence. The total deflection of the system is equal to the sum of the deflection of individual springs. Sum of the deflection of the individual springs. Okay. Let us have distance moved by the mass x for the application of F. Okay, we are going to apply the force F. The deflection is x. Okay, the distance moved by this mass is x. So the total deflection x, this is the total deflection. Okay, this total deflection is nothing but the deflection in K1 plus deflection in K2. Is it okay? But force is same for both K1 as well as K2. K1 is equal to K2. The force in K1 is equal to K2 because it is in series. But X is the total deflection is equal to deflection in the first spring plus deflection in the second spring. So that is the first sentence. Okay. Therefore, in general, total deflection is equal to X1 plus X2 plus X3. If you have three spring X3, general equation I'm going to write X4 plus dash dash dash. If you have more than two springs, this is a general equation. Okay. Therefore, what is a deflection? Total deflection is equal to what is force? Force is equal to spring force. So the effective force is equal to K effective into X. The spring constant to deflection is nothing but spring force, right? Therefore, here I'm going to write it as force. Force is same for all spring divided by, what is that force? What is X? X is equal to force divided by KE, correct? This is KE is equal to, what is X1? Spring 1. Here the X1 is equal to, or F is equal to, for spring 1, F is same for all spring. Okay, F is equal to, force is equal to X1 into K1, right? K1 for the first spring. K1. Therefore, here force divided by K1. Similarly, what about X2? X2 force is equal to, applied force is equal to K2 into X2. Therefore, X2 is equal to force divided by K2. Therefore, force divided by K2. Similarly, for third one is also force divided by K3 plus dash dash dash. Here force is same for all the mass, all the springs, right? you may have 3 spring, 4 spring, whatever it may be. Force is same for all spring. That's why force into stiffness into deflection, right? But the deflection is different for different spring. That's why I've taken it as force divided by K1, force divided by K2, force divided by K3. See, this force will be get cancelled. It's a common term in both the side. So what will be the final answer? 1 by Ke is equal to 1 by K1 plus 1 by K2 plus 1 by K3 plus dash dash dash. So this is what the general equation for the springs in series. General equation for the effective spring stiffness when the springs are in series. Springs are in series. Any doubt in this concept? Any doubt? This is for K2, this is for K, this is for K1. Here you can write it as K1 is equal to force divided by X1. You can write it. Copied? Hello, copied? Can anyone answer?
Yes, sir.
Okay. Write down the next sentence below that. You need to write the significance. Write down. Thus, when the springs are connected in series, when the springs are connected in series, the reciprocal of the equivalent spring stiffness, is equal to the reciprocal of equivalent spring stiffness is equal to the sum of the reciprocals of individual spring stiffness. Sum of the reciprocals of individual spring stiffness. Sum of the individual spring stiffness. That is the final statement when the springs are in series. Any doubt in this? Hello? Any doubt? You should take both the cases, spring in series as well as parallel. Spring force is equal to what it is? K into X. Deflection into spring constant. This equation you need to make use of both parallel as well as series. Okay? Okay. Next. Okay. Next heading, write down. Effect of, next heading, write down effect of mass of spring on natural frequency. Natural frequency. Very, very important derivation. Effect of mass of spring on natural frequency. the last class, we have derived equation for the spring mass system. We have considered only M. Let us consider this is a spring mass system. We have a mass. We have considered only this mass, right? We have not considered the mass of the spring. You consider this mass of the spring in the previous derivation? No, we have not considered. We have considered only the mass or the external mass applied on a spring. We have not considered the mass of the spring. So spring will have its own mass. We have not considered it, but we need to consider it. We'll get an actual or accurate value of or accurate equation for the natural frequency. So in this derivation, we are going to consider the mass of the spring also. Is it okay? Write down below this. Do it fast. Let L be the length of the spring. Let small l, okay, small l. L be the length of the spring. Length of the spring under equilibrium condition. Under equilibrium condition. Full stop. Consider an elemental length of spring. Consider an element. Consider an element. Consider an element dy of the spring dy of the spring at a distance of y from the support. If m dash is the mass per unit length of the spring, in equilibrium condition, then the mass of the spring, the total mass of the spring is equal to, that is ms, total mass of the spring is equal to m dash into length of the spring, right? M dash into length of the spring. So what is m dash? M dash is the, let us have a spring, okay? This is a spring. Total length of the spring is L, okay? Yes, given it is L, and unit length has taken, that is dy, okay? And at a distance of y from the fixed end, at a distance of y, you have taken a unit length, and the spring, if you consider m dash, is a mass per unit length, okay? But total length into mass per unit length will be giving the total mass of the spring, that is ms. Total mass of the spring is equal to ms is equal to m dash unit length into total length of the spring. That will gives you the mass of the spring, total mass of the spring. Copied? Don't copy the figure. I'll give you the figure later. Hello, copied? Open your mouth.
Yes, sir.
Okay. I hope you copied. Let us go to the next slide. Okay. Here I'm going to give a figure. Please copy this figure. We have mass. Okay. That is a spring. There is a spring. Okay, here we have a mass connected to the mass, external mass. Okay, here we have a spring. Right, spring, and total length of the spring is L, small l. Okay, and the stiffness of the spring. Okay, let us consider a unit length. Okay, or a elemental length. This is what my elemental length. So elemental length is, see, this is what my elemental length, that is dy. A small element I have taken dy, but this dy or the element is taken at a distance of y from the top end. This is y. From the top end or fixed end, I have taken y distance. At that distance, I have taken an elemental length dy. Total length of the spring is L. And we have a spring stiffness K. This is K. Spring stiffness K. And the mass is moving at a distance of x. Mass is moving at a distance of x. Or the deflection of the mass is x. Finished? Hello?
Sir.
Yes. I hope you finished to copy the figure. Do it neatly. Write down. At any instant, let the mass be displaced from the equilibrium position through a distance x, then the potential energy of the system is given by please copy this, do it fast. Now, what is the potential energy if the system is moved to a distance of x? X is an instant distance. Okay, we have applied a load. Due to that load, there will be a deflection of x at any instant x. At that point, now what is the potential energy equation we have done in the last derivation? Potential energy equation, second method. What is the potential energy? Potential energy is equal to half into k into x square, right? I'm going to write it directly, but actually we have to take it in the graph of deflection or a spring force. F versus deflection x. correct? Graph, that graph. So this is what the graph. Yeah, this is what the graph. We have x distance, we have moved to x distance. The spring force F is equal to K into X. K into X. So potential energy is a area under the curve. How do you find out the area under the curve? Area under the curve is equal to half into, area under the curve is equal to half into
F into X.
half into what? Base X into
X.
height kx, correct? So answer will be half into kx square, that I have written directly, is equal to potential energy half into kx square, that I have directly written. You want, you can copy it, the graph and the equation, otherwise you can directly write it, no problem. Okay, that is the first equation. First equation, equation number 1. Now the kinetic energy, write down the kinetic energy Ke of a vibration system at this instant. At this instant consists of kinetic energy of the main mass plus kinetic energy of the spring. See, in the last derivation, what we have considered only the main mass. What we have taken in the last derivation, we have considered Ke is equal to half into mv square. We have considered only the main mass. But in this derivation, he is telling that you consider the mass of the spring also. Mass of the spring. Because the spring is having its own mass. And while moving, it experiences some velocity. If there is a velocity, spring mass into velocity, that will have its own kinetic energy. The spring will have its own kinetic energy. The mass will be having its own kinetic energy. Spring, if you consider, the spring is also experiencing some kinetic energy. So that's why we need to consider the spring kinetic energy as well as the main kinetic energy, or the kinetic energy due to the main mass as well as the kinetic energy due to the spring. We need to consider both. That's why I have given this sentence. What it says, we need to consider the kinetic energy of the vibrating system at this instant consists of kinetic energy of the main mass plus kinetic energy of the spring. We need to consider both, not a single. But in the previous derivation, we have considered only a main mass, kinetic energy due to the main mass. But here we need to consider both main mass as well as spring mass. Is it okay? Okay. Now, kinetic energy of the main mass. Write down. Kinetic energy of the main mass. Kinetic energy of main mass. What is that? It is equal to, kinetic energy of the main mass is equal to half into mv square. That is understood. Equation number 2. Kinetic energy of the main mass, you know that. That's why you can directly write that is half into mv square. We have considered the main mass. Next, copied or not? Hello? Open your mouth.
Yes, sir.
Okay, let us go to the next slide. Now we need to find out the kinetic energy of the spring, because spring is having its own mass, correct? A spring is also a moving element, right? See, this is a spring. If you apply the force on mass 1, the M1, main mass, it moves down, as well as the spring is also moves down, right? Up and down motion will be there for the spring. If there is a up and down motion for the spring, then there will be velocity, right? If there is a velocity, then there will be kinetic energy. Am I right or wrong? Right? Kinetic energy will be maximum at the equilibrium position, but it is zero at the extreme end. We have not reached to the extreme end. We have considered only x distance at any instant. X is nothing but at any instant. If the x is equal to a, then kinetic energy will become zero. But it is not, now it is not equal to a. Still is moving in the downward direction. So at this point, the system will have both kinetic energy as well as potential energy. We have an equation for potential energy, that is half into kx square. Now the kinetic energy, half into mv square, it is only due to the main mass. We need to consider the mass of the spring also. Mass of the spring also, because the derivation itself is consider the mass of the spring. What will be the natural frequency? If you consider the mass of the spring, we can write the equation for kinetic energy. So kinetic energy of the mass spring, write down the kinetic energy. The kinetic energy of the spring I'll write it as kinetic energy of the element dy of the spring. I'll consider only the elemental length. Okay, I will not take total length. I'll take elemental length first. Is given by, is equal to kinetic energy of the element dy is equal to, please look at this, I have taken only dy distance from here to here. Okay, so at that distance it's having its own mass, right? Dy distance will have its own mass. So due to that mass, what will be the kinetic energy? And I will integrate it so that I'll get the total kinetic energy of the spring. Okay, so elemental length is equal to half into, you know what is kinetic energy? Kinetic energy is equal to half into mv square. Now what is m? M is the mass of the elemental spring. We have considered only the elemental length dy, elemental length. So mass of elemental length. Now what is the mass of the spring? We have considered mass of the spring. It is having total mass as ms, but unit length, mass per unit length is m dash. So here you can write it as m dash. Otherwise you can write it as mass of elemental spring into half into mass into velocity of elemental spring. That is what the kinetic energy equation, half into mv square. What is m here? Mass of the elemental spring, because we have considered the kinetic energy of elemental length into velocity of the elemental length. Now I'll write it again, half into what is the mass of the elemental length or elemental spring. So mass per unit length into dy, length of the elemental length, into, understood this concept? M dash, what is m dash? Mass of the spring per unit length. What is dy? It is the length of the elemental length, or it is the length of the elemental spring. So unit length into length of the elemental spring will gives you the mass of the elemental spring, right? Into velocity of the elemental spring. What is the velocity of elemental spring? Here it is y by L into V. This is very, very important. Square. This is square, okay? Velocity square. I'll tell you why it is y by L into V. This is very, very important concept. Okay. All of you copied this? Please copy this. I'll tell you why it is y by L into V. I hope you understood the first concept, that is m dash into dy. M dash is a length of the spring per unit length, or mass of the spring per unit length, into length of the elemental spring. That will give you the mass of the elemental spring. I hope you copied. I'll explain what is y by L into V. Copied? Hello? Hello? Copied?
Yes, sir.
Okay. Is there any doubt till this mass of the elemental spring? I'm explaining the last term, okay? Open your mouth. Any doubt?
No, sir.
No.
No, sir.
Okay. Very good, very good. Okay. Now I'm explaining y by L into V. You know what is V, right? You go back to the previous slide. Here, kinetic energy of the main mass is equal to half into mv square. What is this V? V is the velocity of the main mass. Right? Where is this main mass? Main mass is connected to the end of the spring at this point. This point will experience a velocity that is V, maximum velocity. V, the velocity will be maximum at this end of the spring. Why? Because the end of the spring will experience more displacement, or the maximum displacement. Where the displacement is maximum, at that point will have maximum velocity. So V is the velocity of the end of the spring or the main mass that we have considered here. Okay, V into, what is it? Y by L. What is Y? Y is a distance from the fixed length to the elemental length. Fixed length is this one, fixed length of the spring. So this is what the distance. Here we have considered y length, dy length, elemental spring. This is what y length, or the distance between the fixed length to the elemental length. Correct? So y by L, what is this y by L? You look at this figure, here the velocity is maximum, that I told you. Why it is maximum? Because it experiences maximum displacement of x. X goes on decreasing and will become 0 at this point. X is maximum here, maximum displacement, and goes on reducing and it will become 0 here. Is there any displacement for this point? No. Fixed point, there is no displacement for the spring. But the displacement is gradually increasing and will become maximum at this point. Okay? At the same time, as the displacement is maximum at 0 here, velocity will be maximum at this point, that is V, and it gradually decreasing and will become 0 at this point. So the velocity at any point at y distance is always y by L, because we need to take the fraction of the velocity. The fraction of velocity, or the velocity is gradually decreasing and it is a fraction of y by L at y distance. So because as y increases automatically, so if you take elemental length at y as this distance, so y by L ratio increases, right? As a result of increasing the y by L ratio into V, y by L ratio, automatically V also increases and it will become y, and y goes on increasing. When it becomes L, y is equal to L, what happens? Y by L, it is equal to L by L, y is equal to L, right? At the end, L. So this will be 1, y by L become 1, means velocity will be maximum. V into 1, it is nothing but a maximum velocity. So as you increase y, velocity also increases. Increasing y means moving downward direction. So as y increases, automatically y by L ratio increases. As a result, v also increases. That's what our significance, or what that's what we have discussed. So v increases gradually and it will become maximum at the end point, or mass point, or the point at which the mass is fixed. So y is taken as y by L ratio. So it is a fraction which is multiplied to v, maximum velocity. Why? Because velocity gradually increases as you move towards the mass. So that's why we have taken y by L ratio. Is it okay? So y by L ratio into the maximum velocity. Okay. So when the velocity will be maximum, when y is equal to L. If the elemental spring moves here, then y will become L, and L by y by L ratio will become 1, and the velocity will be maximum. That is the significance. Okay. Next, we'll write it equation here, y by L into v. That is the velocity at any instant or at any point, okay, on a spring. Okay. So after that, total kinetic energy. Now we have taken only for the elemental length, right? Now total kinetic energy is equal to total kinetic energy of the spring is equal to integration of 0 to L of kinetic energy of the element dy. So it is equal to integration of 0 to L. Why it is 0 to L? Total length of the spring. The kinetic energy of the total length of the spring we need to consider. We have considered only dy distance, but here total length into what is the kinetic energy of the element dy is equal to half into m dash into dy into y by L into v whole square. It is equal to 0 to L half into m dash into y square by L square into v square into dy with respect to dy. Here half is a constant, m dash is constant, y is a variable here. Y is a variable because y can be varied. L is a constant, length of the spring is constant, v is also constant because the maximum velocity is constant. Next, copied. Integrate this half into m dash into, what is that? M dash into L square, 1 by L square, right? Into V square. Integration of 0 to L. What is this? Y square into dy. It is equal to, answer, half into m dash into 1 by L square into V square. What is this? Y cube by 3, correct? 0 to L. It is equal to half into m dash into 1 by L square into V square. What is this? Sorry, L cube, right? L cube by 3 minus 0, right? So L cube by 3. See here, L cube, L square get cancelled. It is equal to half into m dash into V square into L by 3. Now, what is this M dash per unit length into L? What is this L? It is equal to half into M dash into L is nothing but, what is that? V square into, what is this M into L? M dash into L, unit length per into length, total length. That is MS, correct? MS by 3. So it is given right here. MS is equal to M dash into L. Sorry, MS is equal to M dash into L. So this is equation number 3, correct? Two agide, 3. Understood? Bega bega madbeko, time up, do it fast. Copied?
Okay.
Next,
Yes, sir.
not copied? Do it fast, do it fast. Next, total kinetic energy of the system. Total kinetic energy of the system is equal to kinetic energy of main mass plus kinetic energy of spring. Means equation number 3 and 4. Add equation number 2 and 3, right? I hope you finished. It's equal to total kinetic energy is equal to. So the first main mass half into mv square plus, what is this equation here? Half into v square into ms by 3. It is equal to a common term, half into here m plus here ms by 3 into v square is also common. This is equation number 4. Write down according to the Newton's law, or it is called as energy method. What it says, energy method, potential energy plus kinetic energy is equal to constant, that we have done in the last derivation. Second method, potential energy plus kinetic energy in a system at any instant is equal to constant. So kinetic energy will be converted to potential energy will be converted to kinetic energy. But at any instant, the total amount of energy is constant. So what is potential energy? Half into kx square plus kinetic energy half into m plus ms by 3 v square is equal to constant. Is equal to constant. Differentiate equation with respect to time. with respect to time or dt. Copied? With respect to dt. Another 2 minutes, do it fast. Differentiate equation with respect to dt. Low. First, differentiation hop into kx square. All of you copied this slide?
Yes, sir.
Okay. Differentiation of half into kx square. So half into k is a constant, x square, differentiation of x square with respect to time. 2 into x into what? Dx by dt plus second term half into, this is constant, right? ms by 3 half into m plus ms by 3 constant v square, that is 2 into v into dv by dt is equal to 0. Differentiation ನಿಮಗೆ ಮಾಡೋದು ಬರುತ್ತೆ ಅಂತ ಅಂದ್ಕೊಂಡಿದ್ದೀನಿ. You know how to differentiate this equation, so I'll directly write it here. So here 2 will get cancelled, 2 will get cancelled here, right? I'll write the equation, final equation. Look at this. So k x, this is what v, correct? Last equation. Okay, so v plus here m plus ms divided by 3 into v into what is dv by dt, a is equal to 0. Here v is a common term, will get cancelled. So the final equation kx plus m plus ms by 3 into a is equal to 0. Okay, therefore here a plus k by m plus ms divided by 3 into x is equal to 0. So divide this equation by m plus ms by 3. That will push to that side, and here this term will get cancelled in the second term, and kx, this is the equation. Equation number 5. For SHM, you know the equation, right? For SHM, what is the equation? A plus omega n square x is equal to 0. 6. Compare the equation. Compare the equation. Here, what is this? Omega n square. Omega n square is equal to, compare equation 5 and 6. What it says? Omega n square is equal to k by m plus ms by 3. Correct? Therefore, omega n is equal to square root of k by m plus ms by 3. What is Fn? Fn is equal to omega n by 2 pi is equal to 1 by 2 pi into square root of K by M plus MS by 3. This is what the final equation. So what is the difference? But we have Fn in the previous equation without considering the mass of the spring. 1 by 2 pi into square root of K by M. But here it is MS by 3 is added to the denominator. MS by 3. What is MS? MS is the mass of the spring. Please copy this. Do it fast. Finished? Hello?